It's a great honor for me. I wanted to talk about a recent program that's been developing for about the last 10 years. And in principle, it should have been developing for the last 100 years, if not longer, but somehow there were no tools available until about the last 10 years. And specifically, I'm referring to the explosion of work in expanders and spectral gaps for non-arithmetic and even thin groups and semigroups. And I want to introduce you to all of these things, but in a very we're going to start at the very, very beginning. So let's do that and recall an old theorem of Apollonius's. So this is 300 BC. Apollonius was interested in, he was studying, among many other things, tangencies. And in particular, if you have tangent, if you have 3 tangent circles, he wanted to know in general position, 3 circles at first in general position, he wanted to solve by straight edge and compass the problem of constructing a circle that's tangent to the 3 given ones. So here's one solution to the Apollonian problem. And a particular instance of so here's another, just in case. So you get the idea. In fact, he wrote something like 8 volumes on this topic of all possible configurations when the circles are points or lines, and inside some circles, inside others, and so on. The volumes were lost, and the only way we even know about them is through a MathSciNet review of Pappus, which describes what's there, but doesn't describe how he does it. In fact, it was only in the 16 or 1700s that people were able to reconstruct Apollonius's constructions through inversion. Viet was among the first. So there was a period where people thought that Apollonius was using some other tools to make these, straight edge and compass constructions. Anyway, so the theorem. Yeah? Okay, thank you. So has anyone solved the exercise? Okay, so the theorem is, the configuration that's relevant to us is if you start with 3 circles, so given 3 circles which are themselves already mutually tangent circles. So that's a picture like this, for example. Given 3 mutually tangent circles, with disjoint points of tangency, I don't want a triviality, there exists exactly 2 circles which satisfy the Apollonian problem, tangent to the given ones, tangent to them. So a solution to Apollonius' problem where there's one here, this is one of the solutions, and there's another one there, and these 2 are the only 2 that solve Apollonius' problem. Okay, this is all very ancient stuff, very classical stuff. So really what you're doing is everywhere you see a curvy linear triangle, you inscribe a circle in it. And once you've done this once, there's no reason not to keep going. And you inscribe one here, and here, and here, and so on, all by straight edge and compass. And you obtain what is called, today is called an Apollonian circle packing, although this object apparently first appeared in notebooks of Leibniz's. Okay, well that's a nice, beautiful geometric object, a fractal in the plane. It has some Hausdorff dimension, 1.30 something. What kind of questions can you ask about this thing? Well, if you like to count things, you can say the radii are getting smaller and smaller, so the radii, so given such a, let's call this Apollonian packing P, or gasket, as it's known. And so for a typical circle in the packing, we can look at its radius, or since these numbers are going to 0, sometimes it's more convenient to have numbers going to infinity, let's look at their curvature. So the curvature of a circle is just 1 over its radius. And then the first question someone who counts things asks when they see this is, what if I put a sieve, a literal sieve, not a number theoretic sieve, a sieve under this thing and shake it around and throw away all the circles that have radii that's too small, all the small circles, how many circles do I have left? In other words, the number, so let's give ourselves a parameter t, and let's count the number of circles in the packing whose radius is at least 1 over t, or whose curvature is at most t. Okay, so to warm up, what I actually want to get to, as I said, is Diophantine problems. But to warm up, let me state an old geometric theorem. So this is a theorem of mine with Hio from 2011, which states that the number of points, the number of circles, is asymptotic to some constant, which we can write down, times the parameter t raised to the exponent delta, where delta is exactly this Hausdorff dimension of this fractal. So delta is the Hausdorff dimension of the fractal. So let me very briefly sketch some of the ideas going into the proof of this because they'll be relevant to what I want to say later. Any questions so far? Everything's clear? So by the way, this number does not depend on which 3 circles you started with, because you see the packing is determined by 3 points on a circle, which is conformally rigid. And so this is an absolute universal, God-given, Greek-given constant, 1.30 something, as I said. Whereas this constant, of course, depends on which packing you start with. You take a packing and shrink it, you get a different constant. Okay, so some ideas in the proof. Well, okay, if you want to study such a thing, you have a whole bunch of numbers going off to infinity. This is a room full of number theorists. Make an L function. So let's try making an L function associated to this packing, given a complex parameter S. Well, what should we do? We want to capture these curvatures, so let's sum over all the circles in the packing, 1 over this curvature to the power S. Exercise, when S is equal to 2, this converges. Actually, let's do the exercise. Another way of writing this, because the curvature is 1 over the radius, it's the sum over all the circles in the packing of the radius to the power S. So when S is equal to 2, the sum of the radii squared is the area, and the total area of the whole picture is at most twice the area of the largest circle, is in fact exactly equal to. So the L function converges there, L function in very, very large quotations. There's no Hecke theory, there's no... and you might be able to smell already from this formulation that the Hausdorff dimension is going to be the abscissa convergence of this L series. And if you make this precise, so what you can actually get almost by definition, there's some work to be done, is an old theorem of Boyd's from the 80s, that this number, so log of this over log t converges to delta. There's like the difference between a Chebyshev theorem and the prime number theorems. As opposed to an asymptotic formula, this gives you this can't see, for example, if the formula was off by logs, as in fact Boyd predicted from computer experiments. Okay, well, so what you would like to get if you want something like this, I should say, by the way, more recent work of my student Vinogradov in 2012, and independently Min Lee and Hio, give a power savings here. So if you're going to get a power savings, I mean, that's a zero-free strip philosophically. The only L functions for which we know how to do that are like the Selberg zeta function. Things that you can understand as the spectrum of something. So we need a spectral interpretation of this L function. So let me show you where that comes from. If we look at this gasket, maybe it's not immediately clear, but there's an entire Kleinian group of symmetries that preserves this thing. So let me point out, if you take any four mutually tangent circles, so I'll take the largest four, 1, 2, 3, and the outermost. Let me call them something. So the biggest one is C1, C2, C3, and C4. And if I so let me ignore C4 for a second and take 3 points of tangency of the other 3 circles. Then I can draw a circle through that by Apollonius' theorem. 3 points that Euclid knew how to do. And let's see what happens if we take the reflection through this. So let's give this circle a name. Let's call it C4 dual, the circle dual to C4. And if we reflect the entire picture through this dual circle, C1, C2, and C3 are fixed, and C4 gets reflected into C4 prime, the other solution to Apollonius' equation, to Apollonius' theorem. And of course, we didn't have to ignore C4. We can ignore C3 and take the 3 points of tangency of C1, C2, and C4. That gives us another dual circle here. And if we reflect through that one, C1, C2, and C4 stay fixed. C3 moves over here, and C4 prime moves over here. And similarly, here's another dual circle through these 3 points of tangency. And finally, there's a dual circle here through these 3 points of tangency. So this is dual circle. This one was C4. This one is C3 dual. This big one was C2 dual. And the innermost one is C1 dual. And I claim that using just these four reflections, you will get the entire packing when you start with the initial 4 circles. In fact, the better way to see this is to think of this as lying on the ground and looking in hyperbolic 3 space. So this is the Poincare extension of circle reflections to sphere geodesic hemisphere reflections. And if you do that, you'll see a picture like that. So if I had a pointer, I would show you that here's C4 tilde, this big geodesic hemisphere, C2 tilde, C3 tilde, and inside is C1 tilde. And what I've done here is instead of taking circles, I just take 1 point in upper half space and move it around under these transformations. So that 1 point gets reflected inside from outside C4, it gets reflected inside C4 tilde. It also gets reflected inside C3 tilde, C2, and so on. And as you can see, the limit set of that orbit recovers the original gasket on the ground in the boundary. So this is the sense in which we'd like to see a spectral interpretation of these things. It turns out that this problem can be converted. So let me say, let gamma be the subgroup, the Kleinian group generated by these reflections. So I'm identifying the spheres or the circles with their hemispheres, which I'm then identifying with reflections through those hemispheres. So this will be a subgroup, in fact a discrete subgroup, of the isometry group of hyperbolic 3 space. And it turns out that a counting problem of circles has just been translated, let me say squiggle arrow, has just been translated into some counting problem about orbits of points in groups. So let me put it this way. It's the number of points in an orbit, roughly. So I'm going to lie to you just a little bit to make things easier. So it's the number of gamma in gamma, so that when you take your favorite base point, let's take the point j. So if I use the variables 1, I, j in hyperbolic 3 space, then if I take the variable j, the point j, and move it around by gamma, it turns out that the relevant thing to study is the height of this orbit, because each point in the orbit if you take a circle and you start moving it around by the orbit, then the radius of that circle is related to how high that circle is off the ground, the highest point off the ground. So the z part in x, y, z coordinates, I need to be at least 1 over t. Let me draw a picture. Tell me if you can see this picture. So I have this orbit. I start with J, and I start moving around, and here are my dual circles on the ground, above which are geodesic hemispheres. And I start moving J around to here, to there, and then it keeps getting reflected. And in the limit, you see this orbit. And so what you really want to know is if you take the plane at height, so if this is x, y, z, I want to know how many of these orbits, how many points in the orbit, I'm lying, but pretend this is what the problem turns into. How many points, it's essentially what the problem turns into. How many points in the orbit have z part at least 1 over t? So I cut off, I take this plane at height 1 over t above the ground, and I only consider, and the counting problem is how many points are there above this plane as the plane shrinks down. Now a plane in hyperbolic 3 space is just a horosphere tangent to infinity. So there's a standard way, in infinite volume it's sort of standard, it's not standard, by now it's standard, 10 years ago it wasn't, of turning these kinds of questions into questions about equidistribution of low-lying horospheres or horoballs. So let me remind you of the more classical setup. So any questions on this interpretation? Okay. Okay, so let me recall the classical picture. What I've drawn here is the fundamental domain for SL2Z acting on the upper half plane, as everyone has seen a million times. We saw it this morning. And here, an infinite, well, a horoball is just a circle. So there it is, a horocycle. And if I take this horocycle and I push it by the positive geodesic flow, so it's really everything's taking place in the tangent bundle. So if I push by the positive geodesic flow, all you do is escape into the cusp and nothing happens. But if you push by the negative geodesic flow, once it gets to a certain point, you should put the horocycle back into the fundamental domain. And you should keep doing this as you get further and further down. And that's what this sequence of images is supposed to be illustrating. So the first one is just at height 2 or something. And once you get down to height a little bit under 1, that's what the reflection looks like. And you go a little bit lower, a little bit lower, a little bit lower. That last picture looks an awful lot like hyperbolic density, dx dy over y squared. So this was an old observation. In fact, it more or less follows from Margulis's thesis. But so let's say in this setting, it's a theorem of Zagier's from early 80s and generalized to arbitrary lattices by Sarnak in SL2R. Also around 81. So how do we make this a mathematical theorem? Well, what does it mean that these horoballs are becoming equidistributed with respect to that measure? It means that if you take some region, let's take a function which is like the indicator function of this region, or some smooth version of it, and if we integrate over this horoball, so let's call this a horoball at height y, so if we integrate over the horoball of height y of this function, in other words, how much time are we spending in this region, relative to the length of the horoball. It doesn't look like the horoball is getting longer, but that's because we're looking at it in Euclidean space. The integral is, of course, of length y. So the measure here is dx dy over y squared. So this object should approach as y goes to 0, as the horocycle falls closer and closer to the ground, it should approach the total proportion of this area, which you can measure by integrating f over the fundamental domain. So gamma is now SL2Z, relative to the volume of this quotient. Okay, so this is an old statement. very well understood. In fact, the rate is even understood. You can prove a rate that's something like y to the half plus epsilon. I'll ignore epsilons throughout this talk. And in fact, this is a cute observation of Zagier's that if you can improve this epsilon, if you can improve this 1/2 to 3/4, that's equivalent to the classical Riemann hypothesis. So if the rate is faster than the rate you can prove, you can actually prove little o of y to the 1/2, which is equivalent to the prime number theorem. Okay, but let me ignore that and go back to the asymptotic. So this is a well-understood phenomenon, and it's well understood how to use these equidistribution statements to then recover counting statements of this form. So the only issue that remains for us is to prove a theorem like this in our setting. Now let's just see what it's supposed to say. If we integrate over this infinite Horo ball, normalized by its length, and flow down, what we should recover is the total area of the region. So F you think of as being compactly supported. The total area of the region relative to the volume of the domain. Now let's just do a couple of calculations. What's the volume of the domain? Well, what's a fundamental domain for this action? It's just everything. This is a Schottky group, so it's just everything outside of these 4 geodesic hemispheres. That has infinite hyperbolic volume. And so the statement will now say that the quantity on the left approaches 0 as y goes to infinity. It's not false. What that will tell you is that this is little o of t squared, not asymptotic to t to the 1.3. There's a much worse problem, which is that 1 over the length, well, what is the length of any fixed Horo ball at height y? It's an infinite Horo ball to begin with. So that's infinity. And 1 over the length is then 0. So the statement is 0 is asymptotic to 0. It's true, but utterly useless. So let me try to reinterpret this statement in another way, which will be useful for us. Any questions so far? Okay, let me move the length to the other side. So let's start with an integral of f over the Horo ball, and it should be asymptotic too. If I move the length to the other side, that's the same as the integral over the Horo ball of 1. That is the length. And let me rewrite the integral of f over the fundamental domain as the inner product with respect to this L2, with respect to his Hilbert structure, of f against 1. And let me write the volume as the inner product of 1 with 1. And it turns out what you need to do is understand what 1 is. So let me try to describe what 1 is. Recall, in this classical setting, we have the square integrable functions on this quotient, and we have the hyperbolic Laplacian, which acts on smooth functions, and it has a unique extension to all of L2. And we have the Selberg spectral expansion of this. So the spectrum, if we normalize to be positive, looks like this. There's this magic number 1/4, above which you have the 1 Eisenstein series corresponding to the cusp. You have the constant function with eigenvalue 0. And then you have, this is Weil's law, you have this embedded spectrum, discrete spectrum, embedded in the continuous spectrum. And for SL2Z, we do know that there's no exceptional spectrum, but the Ramanujan conjecture asks what happens as you move from SL2Z to its congruent subgroups. Okay, so this is all pretty well understood. What happens in infinite volume? So let me use the same letters, but of course, now I mean this gamma. And in hyperbolic 2 space, instead of hyperbolic 2 space, I mean hyperbolic 3 space now. Again, you have a hyperbolic Laplacian acting on this space. This was studied in particular by Lax Phillips. I guess I should say Patterson first. Patterson, Lax Phillips, and Sullivan. And a combination of their efforts tells you the following picture. So now we're in 3 dimensions, so the number 1/4, there's just a change of parametrization. 1/4 turns into 1. What happens above 1? The spectrum is purely continuous. There is no embedded discrete spectrum. There are no Moss forms on this space. That's very easy to prove in the infinite volume setting, and it's in fact consistent with the Philip-Sarnak philosophy that if you perturb in Teichmuller space away from an arithmetic lattice, the Moss forms disappear. Here it's a theorem. Let's talk. So, what's the multiplicity of the continuous spectrum? Well, you're supposed to have an Eisenstein series every time you touch the boundary in the fundamental domain. And here there's a continuum of boundary. So each of these, so there's a continuum. The multiplicity is not just infinite. Okay. How about the base eigenfunction? The base eigenvalue 0 corresponds to the constant function. The constant function is not square integrable on this space. So this is really quite a delicate situation. And what Patterson-Sullivan theory tells you, so Lax-Phillips proved the following picture. Above 1, it's purely continuous spectrum. Below 1, there can be a finite number of eigenvalues. And what Patterson and Sullivan prove is that the lowest eigenvalue, this lambda naught, has a beautiful relation to the Hausdorff dimension of the limit set of this group action. And the relation occurs if and only if, there exist any eigenvalues in this range if and only if this Hausdorff dimension is at least 1. Fortunately, we're in that setting. And if the dimension is at least 1, then lambda naught is related to delta by the beautiful formula delta times 2 minus delta, which is the analog in 3 space of s times 1 minus s that you're familiar with in 2 space. Okay? So now I can tell you what 1 is. 1 is the constant function corresponding to the base eigenvalue 0 in this space. And what you should do instead is measure, so of course, being discrete spectrum, the definition is that there exists an L2 eigenfunction, phi naught, on this quotient, square integrable, with this eigenvalue lambda naught. And 1 is the base eigenfunction of L2 of the modular surface. And what you should do here, so this is the theorem that we prove, it's asymptotic to the inner product of f against phi naught. Let's normalize phi naught to be L2, have L2 norm 1, and you should integrate the Horo cycle over phi naught. So that's the theorem. Once you have this equidistribution of low-lying Horo spheres in infinite volume, where the Horo spheres themselves are infinite, I won't say very much at all about how this is proved, then you, by somewhat standard techniques, recover the counting statement for the orbit from which you recover the counting statement on the circles. So just to illustrate this equidistribution, let me show you the picture. So again, there's our fundamental domain, and I've taken a Horo cycle at height 1. And you start pushing this Horo cycle down, and once you start leaving the fundamental domain, you reflect back into the fundamental domain. And it's hard to see, but when you get down here, these points are supposed to be filling out space. So they're getting blown up all over the place. Obviously, you just don't see anything. Now, you should be arguing with me. Look at this little sliver right there that's just falling straight to the ground. It's never going to touch the fundamental domain. How can you tell me that there's chaotic behavior? This is supposed to be equidistribution. It's just falling straight down without ever interacting with the group action. Remember, it's equidistribution with respect to this base eigenfunction. And in order to be square integrable on an infinite volume space, that base eigenfunction had better be vanishing very, very rapidly as you approach the boundary. So those points just don't count in this asymptotic. Any questions? Question? Okay. Well, that's the sort of analytic and geometric aspect to this problem, but there's lying underneath is a much, more beautiful to number theorists maybe. There's a beautiful aspect to it, which was discovered actually in the 1930s, surprisingly. This gentleman, Frederick Soddy, was interested in building a machine which had very low low friction. And he discovered that one way of doing this was by building the machine out of spheres, tangent spheres. And when you take these tangent spheres, it's basically the three-dimensional analog of the Apollonian construction that gets you these tangent spheres. And he physically built this thing. So to physically build this thing, he had to compute the numbers. What curvature do I need, what radius do I need for this sphere versus that sphere versus that sphere? And he noticed an amazing property which also held for Apollonian circle packings. So let me describe it to you. Here's an elementary exercise. Let's go back to the circle packing. I've taken a circle of radius 1 and divided it by two circles whose radius is 1/2, so curvature is 2. Exercise, when you do your geometric construction to inscribe another circle into the curvilinear triangle, you get radius 1/3, curvature 3. And when you keep going, you get curvature 6, 11, 14, 18, 27. These are some numbers. And the question is, wait a second, to get that third circle, I did a complicated straight edge and compass manipulation. Where's the pi or the root 2 or so? Why are these all integers? Well, maybe it's a fluke. Maybe this is the only time this happens, and it's just a very special configuration with extra symmetries. Here's another configuration. So I've taken two lines. These have radius infinity, curvature 0, and put one circle in the middle, and you see the forward circles touching the ground. Well, maybe it's just those two. No, there's an entire family. There's an infinite collection of... You see, it's funny. Apollonian circle packings geometrically are rigid, as we already said. There's only one circle packing up to conformal transformation. But when you look at the rational structure, it's sort of like what goes on with elliptic curves. There's this beautiful picture. So this is, let's see, the outermost circle has curvature -10, I think. Yeah, -10. Negative because the outermost circle has opposite orientation to be internally tangent. So you have a circle of radius 1/10, a circle of radius 1/18, 1/23, 1/27, 1/62, and so on. Okay, so this is a general phenomenon. And this is what Soddy observed. Okay, once you observe something like this, you give this problem to a bunch of number theorists. So a series of papers by Graham, Lagarius, Mallows, Wilkes, and Yan starting in around 2002, 2003, began an intensive study of the number theoretic properties of Apollonian gaskets. And they formulated the following wonderful conjecture. Okay, so we're a bunch of number theorists. We're staring at a bunch of integers. The first question that arises is, what numbers are we seeing? Now, some of you are very fast and very sharp, so maybe you've already seen. So let big K be the set of curvatures that arise in such a gasket. So let's fix this to be our gasket. So let script K be all the curvatures as we range over all possible circles in the packing. And what you might observe is that you will never see a curvature that's divisible by 24. Tell me if I'm right. Okay, looks like that's okay. So observation. There are some local obstructions. So for this packing, the set of curvatures will always be congruent to either 2, 3, 6, 11, 14, 15, 18, or 23, mod 24. These are the only residue classes in which you'll find circles, and you'll find circles of each of these residue classes. I said that the outermost circle had curvature -10. And 14 is -10 mod 24, so that's okay. We need the orientation. If we didn't have the orientation, 10 is not on the list. Okay. Well, you observed a local obstruction. Why not conjecture a local to global principle? So this is their conjecture. So this is the local global conjecture for Apollonian gaskets, formulated by these 5 authors. Given such a, so the packing is always fixed beforehand. One thing I should point out is, okay, the number 26 is admissible because it's 2 mod 24, but we just don't see a circle whose curvature is 26 because it's too small. We haven't gotten there yet. So there's one more obstruction, which is the obstruction at infinity. So the statement is, every sufficiently large so there's our obstruction at infinity. Admissible. Admissible means lying in one of these residue classes. Integer appears in the set of all curvatures. So that's the local global conjecture. Every single admissible and sufficiently large number is a curvature. You will see it somewhere in the packing as you zoom in far enough. Is the statement clear? Okay, so what I'd like to actually talk about okay, is a theorem with joint work with Jean Bergin from last year, which proves almost every admissible integer is in K. So what does almost mean? I.e., okay, so let me call the set of admissible numbers script A. So script A is the set of all numbers that satisfy, all integers, positive, negative, that satisfy these conditions. So what we prove is that if you look at how many curvatures there are up to n versus how many numbers there should be, how many admissible numbers there are up to n, that goes to 1. In fact, with a power gain, so it's equal to 1 plus big O of n to the, with a power rate. Let me tell you a little bit of, so is the statement clear? Let me tell you a little bit of history on this problem. The previous work, so previously, in fact, these 5 authors made the first progress towards the conjecture. So Graham, Lagarius, Mallows, Wilkes, and Yan proved that the number of curvatures up to n is at least n to the half. Okay, so at least square root of the numbers. Of course, okay, let me reformulate this. The number of admissibles up to n is trivial because there are 8 residue classes mod 24, so 1 in every 3 numbers is admissible. So this asymptotic should be the number of points in K up to n is asymptotic to n over 3 plus a power savings. So n should be the main term. They've proved root n. At least root n numbers appear. Then Sarnak, in a letter to Lagarius on his website in 07, so this is 03, Sarnak proved that this is at least n over root log n. Just barely missing positive proportion. And then Bergin and Fuchs in 2010 improved it to positive proportion. And now we have the asymptotic formula. This is still very, very far away from the conjecture. Let me not understate that. Okay, so let me describe a few of the ingredients in the proof of our theorem and these theorems. But first, maybe I should explain why is this happening, right? We never understood why these numbers are all coming out integers. So let me try to illustrate that. Any questions so far? Yes? Yes?
Do you have any idea of the proportions in the different classes?
Yes, there's a Shibatarov type theorem here as well. I'll explain that. I'll explain that in a sec. So save your question for about 5 minutes. Is there another question? Yes? the number 24 is universal? It's an excellent question. I'll explain that in just a second. This was worked out in Elena Fuchs's thesis. So also save your question for about 5 minutes. The number 24 is universal. These numbers depend on which packing you start with. I'll explain. Other questions? Okay. So what's going on? What's going on was initially observed by Descartes. So here's an old theorem of Descartes from 1640 something, let's say 3. It says if you have 4 mutually tangent circles, given circles C1 through C4 mutually tangent, their curvatures, kappa 1 through kappa 4, lie on the cone Q equals 0, where Q is the quadratic form, quaternary quadratic form, sum of the squares of the entries, actually twice the sum of the squares of the entries minus the sum of the curvatures squared. So this is an integral quadratic form in 4 variables. What do you think its signature is? 3-1. 3-1. It has to be hyperbolic 3 space, right? So what does this mean? What's the consequence of this? In fact, so this theorem, according to Wikipedia, is like Saudi's theorem or something. So Saudi rediscovered this fact and generalized it to higher dimension. I guess I could say now, yeah. Let me state one more theorem before I go on. I'll save it for later. So what's a consequence of this theorem of Descartes? Suppose you give me kappa 1, kappa 2, and kappa 3. So, given kappa 1, kappa 2, and kappa 3, well, you have a quadratic equation for kappa 4. That's 2 solutions. That's Apollonius' theorem. Given 3 circles, there are 2 solutions to the Apollonian problem. This is the Apollonian problem reformulated. Moreover, so you have these 2 solutions, kappa 4 and let's say kappa 4 prime. And of course, everybody knows how to solve a quadratic equation, negative b plus or minus square root. There's this annoying square root there. But there's a plus or minus, so if you add the 2, the square root dies. And you can give this exercise to a 9-year-old. The sum of the 2 solutions is twice kappa 1 plus kappa 2 plus kappa 3. And this has profound consequences. So what does this mean? Hence, if you take the curvatures, kappa 1, kappa 2, kappa 3, kappa 4, and you would like to obtain the curvatures, leave the first 3 alone, but replace kappa 4 by kappa 4 prime, you can do that by multiplying by a matrix, which leaves kappa 1 alone, kappa 2, and kappa 3 alone, and instead of kappa 4, I want 2 kappa 1s, 2 kappa 2s, 2 kappa 3s, and minus 1 kappa 4. Let's call this matrix C4 tilde. Because what it's doing is, algebraically, is exactly the same thing as what C4 tilde was doing geometrically when it left 3 circles alone and flipped 1 to the other equation, to the other solution to this equation. Is that clear? Now, of course, you don't have to flip the 4th guy. You can flip the 3rd or the 2nd or the 1st. So then we get a group gamma. So let gamma be the group defined by these 4, C1, C4, C1 tilde through C4 tilde, these 4 4x4 matrices with integer entries. Now, observe that each of these matrices, by construction, preserves this original quadratic form. So this is a subgroup of the orthogonal group preserving Q And as we just said, it has integer entries. So how do you get more curvatures? Starting with the first 4 curvatures, negative 10, 18, 23, and 27, for example. Any 4 will do. Any 4 mutually tangent circles. You apply this group, and the orbit, so the orbit, we're nearing the word orbit. The title was Diophantine Problems in Thin Orbits. So the orbit is you take this group of 4 by 4 matrices and act on your favorite so-called root quadruple, starting quadruple. So negative 10, 18, 23, and 27. And the set of integers arising in this 4 tuple, so this will be a subset of Z4, contains all the curvatures. But these are all integers. So if you happen to get lucky and the first 4 circles that you write down have integer curvatures, it's not enough to have 3. So 3 circles determine the packing, but that 4th circle must also have an integral curvature, and then the rest of them, the machine runs and you get nothing but integer curvatures. That explains all local obstructions once you know that Zariski dense subgroups of arithmetic groups, well, okay, we have to pass to the simply connected subgroup of determinant 1, the spin cover for a strong approximation to apply. But once you have strong approximation, you know that the group mod Q is determined, is basically SO Q of Z mod QZ. You get the full arithmetic group that it could be. It's full Zariski closure. It's a Zariski dense group is all I'm trying to say. It's a Zariski dense group, so you have strong approximation, which tells you what the reductions of gamma are mod Q for every Q. That's exactly what's worked out by Fuchs. And for primes outside of 2 and 3, the mod Q projection is onto. For the prime 2, you get thin groups until you get to the power 2 cubed. After 8, it stabilizes, so the pre-images are the full pre-images. And at 3, it stabilizes immediately, and 3 times 8 is 24. So that's the universality of the number 24. Now, depending on which vector you start with, when you reduce this group mod 24, you just have a finite group. You multiply that finite group by your root quadruple, that determines these admissible numbers. How often each of these numbers appears in that mod 24 reduction tells you the Shibatarov type conjecture of how often you should see each residue class. That determines the proportion of time you'll see the residue class. Okay, so we're nearing a proof. So let me try to describe some of the ingredients. Okay, so any questions on this? We've explained where this integrality comes from, and we see that it's an orbit. Here's the word thin. What's the index of this group in the full orthogonal group? It's the same as the volume, the co-volume of the isomorphic group, which was this reflection group, which is infinite. So this is an infinite index subgroup of this group. That's very dangerous. I mean, the word problem in group is undecidable. So if you give me a matrix, I can immediately decide whether it has integer entries, and I can immediately decide whether it fixes the quadratic form or not. But I cannot immediately decide whether it's a word in these generators. In fact, for this group, there is a reduction algorithm, so I'm lying. But the general problem, it's not clear how you're going to use that to determine which matrices you're allowed to put here to get this orbit. Again, if this was the full group, that's a classical problem, Diophantine problem, on an orbit, because it's just asking, you have a variety. What are the integer points on this variety under this orbit, right? So that's the sense in which this is delicate. It's a thin orbit. It's an infinite index. So this index is infinite. And so how are you going to get your hands on this group? Okay. Before I go on saying more about this, let me go back to Sadi's original problem about spheres. So here's a sphere packing, an integral sphere packing. There's some curvatures, 36, 28, 85, and so on. And you can formulate a corresponding local to global conjecture, which states exactly the same thing. Every admissible integer should be a curvature here. It turns out admissible here is just a condition mod 3. You can have 0 and 1 mod 3, or you can have 0 and 2 mod 3, depending on who you start with. I guess here we have 0 and 1 mod 3. And so this is a theorem of mine from last year. For sphere packings, every sufficiently large admissible integer will arise. Okay. Let me try to say a word about where these are coming from. Okay. Well, these theorems are coming from special elements. So it turns out that the group has unipotent elements. This original group that we started with, if you take C1 tilde times C2 tilde, that's 2 flips of tangent of nearby. It's clear that the group has parabolic elements. You have these little cuspidal regions on the ground. So if you use just the parabolic elements, you'll recover n to the 1/2. What Sarnak observed is that there's actually 2 sets of parabolic elements, and if you use those 2 sets of parabolic elements, the group they generate is isomorphic to gamma 2, the index 2 classical congruent subgroup. And then that's in the spin. I know I'm saying too many words. I'll just say this very quickly for those of you that know these things. You get it. If you don't, I'm not going to use it. There's a spin representation from SL2 into SOQ, which is a quadratic map. And so it turns out what happens, which is why you have the 1/2 here. It turns out that if you have this full subgroup, arithmetic subgroup of this infinite volume group, what you recover is sums of 2 squares, essentially. So then what Sarnak observes is, well, we know how many integers without multiplicity are sums of 2 squares up to n. It's about n over root log n. And from this, he's able to produce primes in here, because Ivanich's half-dimensional sieve produces prime curvatures. We're also using that group. When you go up 1 dimension, this corresponding group in hyperbolic 4 space has an arithmetic 3 manifold sitting inside of it. And when you work through the formalism, that arithmetic 3 manifold, when you apply Sarnak's method, instead of getting a quadratic form in 2 variables, you get a quadratic form in 4 variables. The problem is much, much easier. There we have Klustermann's method. So that's the local. So this is not a complete triviality, but much, much easier. So let me focus on the theorem I just erased with Bergan and try to explain what some of the ingredients are. Okay, so ideas. As I said, we have this orbit. We have this group that we know very little about, and what's something so general it can try to study something this weird? The circle method. So let Rn of n be, let's try to understand which integers arise here. So let's sum over elements in this group of norm at most n. So I just want to compactify the problem. And let's take the indicator function of gamma times this. So let me give this vector a name v0, the base vector of the orbit. Gamma times v0, well, that's 4 numbers. I only want 1 of them. So let's just take, I don't know, the 4th one. Inner product with E4. I want to know when this is equal to the integer n. Okay, so clearly these numbers will be of size capital N at most, and the set Rn is supported on curvatures arising in the gasket. This much is clear? So what's the circle method? You take the Fourier transform of this, so you get an exponential sum, now as a function of theta on the circle from 0 to 1, which is the same thing, gamma in gamma, norm gamma at most n, e to the 2 pi I theta, and then these numbers, inner product of gamma v0 e4. Now, we're going to break, so you recover the representation number by integrating from 0 to 1 the exponential sum. This is people say this is the circle method. This is for elementary Fourier analysis. The circle method is what you're going to do with that integral. You're going to break this integral according to whether theta is very near rational numbers with small denominators or not. And when it's not, you're going to hope to get cancellation. And when it is, you hope that this looks like Sn at A over Q. And then what you observe is that, well, if you have a Q there, it only depends on the residue class of this inner product mod Q. And you can decompose this group according to what gamma mod Q looks like, times and sum over gamma of Q, the principal congruent subgroup of this group. And here, you see expansion, which we haven't seen until now. So let me very briefly say what expansion is in this setting. So remember our picture. Here's L2 of hyperbolic 3 space modulo this group. Here's continuous spectrum at 1. Here's this base eigenvalue lambda naught, and there could be some more. Now, as we change from gamma to gamma of Q, these are finite index subgroups of the group, but still infinite volume groups. We may get new eigenvalues that weren't there. New forms may occur. And as Q gets larger and larger, for all we know, these base eigenvalues start approaching the bottom. The bottom is fixed because they all have the same limit sets. They're finite index subgroups, so they have the same limit set, so they have the same Hausdorff dimension of the limit set, so they have the same base eigenvalue. But the next eigenvalue could start inching in towards it. The fact that this does not happen is the spectral gap theory, and it's only in the last 10 years that techniques have been developed on these infinite volume quotients. First through, there's work by Sarnak and Xu, which was still for lattices, followed by Gambert's thesis, which was the first infinite volume observation of this, and then the breakthrough following on work of Helfgott's by Bergan and Gambert, and then Bergan, Gambert, Sarnak introduced the affine sieve, which is where this circle of ideas came to be born. And in this setting, it's due to Varyu. There's an issue that the sieving people only care about Q square free, but when you're doing the circle method, you need every Q. So there's a uniform spectral gap. These eigenvalues do not come within a fixed region of lambda naught, fixed independent of Q, and that allows you to analyze the major arcs. When you want to analyze the minor arcs, we don't know how to do anything with this exponential sum. We can't get enough cancellation out of it. But we apply Vinogradov's bilinear techniques, and instead of a full integral, a full sum on gamma and gamma, we make a product of two sums, one out of the full group gamma, and one out of that arithmetic subgroup. The arithmetic subgroup allows us to use classical tools to get cancellation in the minor arcs. In the major arcs, as I said, we use this expansion theory. And let me just advertise that this has also been generalized now to Apollonian 3 gaskets, which you can hear about on Friday. My student Xing Zhang is speaking about that. So thank you for your time.